So I'm going to start by making a sample screencast of lecture 2, which is about sampling distributions and how we test statistical hypotheses concerning them. We'll see how this works. The overview of the lecture is what is the content. We'll talk first of all about sampling distributions and the particularly important concept of sampling error, and its links to familiar topics such as the standard error, typically the standard error of the mean, abbreviated SEM, and a really important statistical theorem, a beautiful theorem that lies at the heart of all statistical testing, the central limit theorem. And then we'll move on to hypothesis testing, the standard statistical tests that you've come across in earlier parts of your graduate and undergraduate education, and some basic key concepts: the null hypothesis, one sample tests. We'll introduce some examples. These are the simplest tests we can deal with, really. Talk about confidence limits and different kinds of errors that statisticians talk about, type 1 and type 2 errors. So the reading that's recommended, that's particularly good for this content, is from Howell, chapters 4 and chapter 7. We'll start off by talking about frequency distributions, which are distributions of individual scores, and we'll distinguish those from sampling distributions, which are distributions of statistics that you measure from samples. So in sampling distributions, there are each point in the distribution, each data point is from a sample. You might calculate the mean and plot that. Whereas we're more familiar, we're looking at frequency distributions in psychology across a sample, where each point is from the individual scores. So the individual scores and how they're distributed depends on the nature of the values. So that's, for example, from a dice. If we throw a dice and we count up the scores for 1, 2, 3, 4, 5, 6, the different outcomes, and here are 600 dice, and it's a remarkably even distribution. It's a uniform distribution, and by chance for this particular dice, in the 600 throws there are exactly 100 1s, 2s, 3s, 4s, 5s and 6s, which of course isn't very likely in reality. Normally the numbers would vary a small amount around the expected value of 100, because the uniform distribution means that each of the values 1 to 6 has an equal probability of occurrence, because this is a fair dice. However, this is a more common distribution we see in psychology, something approximating a normal distribution. This would be an example of a sample of 5,000 IQ scores, where IQ is designed so that the mean is 100 and the standard deviation is 15. And many psychological variables, many naturally occurring variables in the real world and environment, follow a broadly normal distribution. So remember a very important point: the sampling distribution is not always equal to the population distribution because of sampling error and other factors. So that's an example here. This is the theoretical distribution, the expected values, but actually in a real sample the numbers of 1s would vary a little bit from 100, as with the 2s, within the overall total of 600 throws. So we can look within a distribution of individual scores and compute things such as the probability, or p-value, of randomly sampling one person with an IQ of 100 or more. In a normal lecture I'd ask the audience to say what it is, but it's actually fairly obvious, because the normal distribution is symmetrical about the mean. So that means in this case there's half the values are above the mean and half are below, so our probability would be 0.5, 50%. Now we can do more interesting calculations that are relevant, such as what is the probability of randomly sampling an IQ score of 130 plus, and we can actually work this out from what we know about properties of a typical normal distribution curve. So remember, for IQ it's been designed so that the mean should be 100 and the standard deviation will be 15. It turns out that 95%, pretty close to that value anyway, of the distribution lies between 2 standard deviations above the mean and 2 standard deviations below the mean. So 95% of the distribution lies in this region here, and the other 2.5% lies either below -2 standard deviations or above +2 standard deviations. So with 130, carefully chosen because it's actually 2 standard deviations above the mean, we know that if we randomly sample from a normal distribution of IQ scores with standard properties, that 2.5% of the sample should have IQ scores above 130. So our probability is 0.025 or 2.5%. So the probability for any IQ can be calculated using the z-score, and we can look it up in a table of p-values for the normal distributions, or as well you can learn using SPSS to use a cumulative distribution function, a CDF, which will calculate it exactly for you rather than looking up particular values in a table. Of course, this assumes the population parameters are reflected in the sample, the mean of 100 and a standard deviation of 15, and that the data are normally distributed.